My name is Isaac Berry. I'm 12 years old, which makes me the youngest student of NYU. I'm majoring in math and plan to graduate by 2026. And this is Dr. Addison. He was teaching the graduate geometry course that I took on the side all the way back in August of 2023.
I'm taking graduate level courses in geometry at Stony Brook University. These are my classmates. The course is taught by my wonderful teacher, Dr. Addison.
Which gave me my first taste of proofs, so that's something that I really credit him for. And so I guess we're just going to be discussing differential geometry. So what is differential geometry, essentially?
So in differential geometry, we study the way that we can do calculus on different types of interesting shapes. So it's a generalization of how we look at Euclidean geometry, so the geometry of three space, but where we're allowed to introduce curvature and things are allowed to bend, you're allowed to introduce different dimensions, that sort of thing.
I mean, it feels like there's almost nothing that you can generalize, since even Euclidean and spherical and hyperbolic geometry all seem so difficult, so different. So I mean, what concepts are you able to generalize to every single kind of geometry?
So it comes down to the idea of curvature, really. That was Raymond's big innovation, was realizing that you can actually compute this tensorial object at every point called the curvature, which takes in two directions and then differentiates in two directions. And this captures a lot of information that for Euclidean geometry, for spherical geometry, for hyperbolic geometry, these are what we call homogeneous, in that you can't tell where you are just by looking at the curvature, because the curvature is the same at every point. But you can change what that curvature looks like at different points, and then you'll get a more interesting shape coming out of it. So all of the things that one does in multivariable calculus all get generalized to higher dimensions and with more rigor in differential geometry.
Oh yeah, when I took that general relativity course at Stony Brook, I had an idea of what the Ricci curvature tensor meant, but I didn't actually get into the specifics, because when my tutor tried to get into it, it just didn't get into my brain. But
yeah, it is very complicated and took a little while for mathematicians to jump on board and decide to adopt it and study it fully. And I think Einstein's work in relativity had a big part in that, because he was applying what I think at the time was called the Ricci calculus to something that was so fundamental. And general relativity is a great place to look at this, actually, because the Einstein field equations tell you that if you have some sort of mass in space, it changes the curvature there. And that's a way to that's perturbing from Euclidean setting to where things are a little bit different there. And you have this curvature that's very curved around the object and then flattens out away from there. So
yeah, so I guess the Euclidean and spherical and hyperbolic geometries are so studied in specific because of how their curvature is just constant.
Exactly, they're the constant curvature spaces.
Yeah, but of course space-time doesn't work like that, because the whole point is that it's curved.
Right, so it was initially interesting because even studying the vacuum equations for Einstein's equations was not super obvious that there would be solutions to this. And Schwarzschild came up with a solution to the vacuum equations very soon after Einstein published his work, and that was a big innovation in the field. But you're right, having mass and other things, and that's going to change the curvature, and you're not going to have a constant curvature space anymore.
I mean, yeah, Euclidean geometry and especially spherical and hyperbolic geometry were pretty difficult for me when I was looking into it. So imagining generalizing that or doing that specifically with non-uniform curvature sounds like a nightmare, but I'm excited to get into it.
It gets even harder though, because everything in general relativity is in 4 dimensions, because you have to include time and space-time, so you can't visualize any of it.
And that's why you assume a 2-dimensional universe is Gaussian curvature. It has something to do with eigenvectors and eigenvalues or something. So what is the basic idea behind Gaussian curvature?
Right, so curvature starts with thinking about a single one-dimensional object that we can think of as curved, right? And the definition of curvature there is you look at the osculating circle, and 1 over its radius is that curvature. Surfaces.
Oh, so like the curvature of a sphere, for example, just 1 over r times 1 over r.
So yes, and on a surface that isn't necessarily as homogeneous as a sphere, at each point there's something you can compute, which are called sort of fundamental curvatures, which arise as eigenvalues, whose eigenvectors are these sort of principal directions that you have, and you compute the Gaussian curvature by taking the product of these two things. And this was Gauss's big innovation in geometry, because this is something you can compute intrinsically to the surface itself just by knowing how to find distances and embed length minimizing curves in the surface. And his whole his incredible theorem, or theorem of Gaussian, is really about how the product of these two principal curvatures is sort of constant in some sense. So this is even present in how one picks up a slice of pizza, that it should be flat. So you could introduce curvature along the crust direction, but it'll need to stay flat in the other direction. So
yeah, I actually heard about this because I'm also a little bit into geography as well. So I heard like you can't map the globe onto a flat plane. And I was always wondering, I mean, why? It seems like it's possible, maybe just like all of the projections we've come up with so far just don't cut it. So I looked into it a bit more, and I saw the theorem of Gaussian, but I didn't like actually get into it. I didn't understand.
yeah, it's this curvature is something that you can't get rid of, but you will learn in your complex analysis class that you can actually what's called conformally map the plane to the sphere or the other direction, where you keep all angles the same, but lengths have to be sacrificed. So that's sort of one of the ways that projections try to get around that.
Okay.